3-2. The differences from today's procedure are fairly trivial. Most probably. 1. We would look for a column, for example, the left one, which could be subtracted from others without first having to multiply them up. 2. We would say we were subtracting twice column 3 rather than saying that we were subtracting it repeatedly. These are details. The method, it could be said, has not changed even if questions about different grades of paddy are less frequent. There is, though, a more subtle difference. Confronted with such a question, a modern textbook would call the paddy yields x, y, and z, form 3 equations, and then write a matrix to solve them. In the history of European mathematics, x's precede matrices by about 200 years. In the 9 chapters, there is no intermediary between the paddy and the matrix. There is indeed what one could call abstraction, but instead of our kind, which consists of replacing unknowns by symbols, it inputs data directly into a solution diagram. This particular kind of abstraction seems to have been peculiarly Chinese. It was clearly tied to the use of counting rods, and so, we could guess, it traveled less well than some other Chinese mathematical inventions. Exercise 4. Follow through the calculations, and check that they give the right answer either by using matrices, or using counting rods, or any other way. 7. The Song Dynasty and Qin Zhoushao. There is no reason to doubt that the last half of the 13th century was the culminating point of Chinese mathematics. In later generations, scholars were very proud of themselves and, considering inferior, did not teach them. Only calculators and mathematicians were able to manage multiplication and division, but they could not comprehend square root extraction or indeterminate analysis. In case there were calculations to be performed in the government offices, 1 or 2 of the clerks might participate, but the position of the mathematicians was never held in esteem. Their superiors left things to them and let them do as they pleased. If those who did computations were only that sort of man, it was merely right that they should be disdained. Subsequent historians have referred to the Song dynasty as a golden age for culture in many respects, and for mathematics in particular. To mathematicians such as Qin Zhoushao, who complained of their treatment as the nerds of the Chinese hierarchy, it did not appear so. The dynasty lost dynamism over a short period, and its territory shrank to the southern half of China, the north being controlled by a rival, a barbarian dynasty, the Jin. In the 13th century, which Librecht describes as the culminating point, the Mongols under Chinggis Khan fought a 50-year war and finally overthrew the Song rulers. They ruled under the name of the Yuan dynasty from 1260 to 1368. The outstanding mathematics for which the period is known is distinctly enigmatic. We have works from 4 apparently unrelated writers from the 13th-14th centuries, the prolific but fairly elementary Yang Hui, and 3 more surprising mathematicians often sharing common concerns, but working in isolation, often with no official position to provide them with problems or support. Their work is both innovative, in that it is clearly different in kind from what has appeared before, and at the same time traditional, in that the models which it draws on are supplied by the classics. 1. Li Ji, who lived in the north, worked under the Jin rulers and later the Mongols, and wrote the eccentric text called Siyuan Haijing, apparently dated 1248. This is entirely devoted to obtaining equations from problems of a geometrical type about a town whose plan is drawn at the outset. The problem is always to find the town's radius. The answer is always 120. Figure 4. Li Ji's around town form the Siyuan Haijing. 2. Qin Zhoushao, who worked in the south, and during a boisterous life wrote the long and semi-practical Shushu Jiuzheng. As well as material which can be found elsewhere, this provides the most advanced source for the Chinese remainder theorem, how to find a number n which leaves remainders a, b, c. when divided by p, q, r. 11. The Shushu Jiuzheng is a complex work, organized around practical problems but often dealing with them in far-fetched ways. Among other things, it illustrates the disturbed politics of the period by some of its questions: how to arrange soldiers in formation, how to find the distance of an enemy camp. At the same time, the mathematics introduced into the solution of the problems seems sometimes to pursue difficulty for its own sake. 3. Zhu Shijie, another northerner, wrote 2 books which were printed but never seem to have been used for teaching. Like the other difficult songwritings, they were probably soon forgotten. The very long Siyuan Yu Jian is, of course, again a collection of problems. However, it is very much more, since the problems lead to sums of series, high-degree equations, in fact a highly organized algebra whose ideas are similar to those of Li Ji. Since it is partly by chance that our key texts from the song survived, there may have been others. Many of the methods, and even the problems seem to have been common, and one wonders why. 11. There is no space to deal with this problem here, or the questions raised by Qin's treatment of it. His results were not rediscovered until the time of Gauss, and are in some respects more general than Gauss's work. 208. Figure 5. Following Chinese convention, south is at the top. B is the point where the walker catches sight of the tree. Other lettering refers to the solution of the problem. To give a particularly striking example, in his Ziyuan Haijing Li Ji gives the problem. 135 pu out of the south gate is a tree. If one walks 15 pu out of the north gate and then turns east for a distance of 208 pu, the tree comes into sight. Find the diameter of the town. Li Ji solves the problem by an equation of degree 4, with the result 240 pu. The picture is shown in figure 5, clearly, its analysis requires more than basic geometry, that a Pythagoras theorem, called gugu by the Chinese, properties of tangents and similar triangles. On the other hand, Qin Zhoushao solves an extremely similar problem by an equation of degree 10. Partly, it is true, by the artifice of using hex for the diameter. There are very strong reasons to suppose that Li and Qin never met or communicated. They lived as near contemporaries in mutually hostile parts of China. The two symbolize 2 kinds of mathematician. For Qin, the world consists of watchtowers constructed on the walls of cities, while for Li, people wander aimlessly round similar cities trying to catch sight of trees. Yet the mathematics is much the same. What is the explanation for this sudden eruption of a school of mathematicians who, working apparently independently, produced work which is both original and in some ways related? A part of the explanation is simple, it lies in our great ignorance. None of the writers, with regard to the work which seems most striking, claims to be innovating, and some refer explicitly to predecessors whose works are lost. The golden age of the 13th century might therefore appear less golden if we knew more of the ages which had preceded it. So, for example, Yang Hui uses the Pascal triangle, but ascribes it to the 11th century writer Jia Xian, whose works have not survived. Even the striking notation for polynomials called the atténuant, or celestial element method, was apparently copied from an earlier lost writer. In Librec's judgment, It is obvious that only a few names have been recorded, and that the greater part of Chinese mathematical works have been lost. Figure 6 illustration from the Shushu Jiuzhang, page 167. We have, as often in the early history of mathematics, an impressive part of a structure which has survived almost by chance while the rest is missing. Failing dramatic discoveries of the texts from the earlier period, we must be content with what remains, and try to understand the aim of this school, which was not a school. While our evidence for a culture of mathematicians during the Song is sparse, the books do seem to aim at a specialist audience, whether it existed or not. Librecht emphasizes both the practicality of the Shushu Jiuzhang. In a splendid work on architecture, the Yingtao Fa, there is a full description of materials and constructions, but what is lacking is plans for carrying out the work, the calculation of the building materials, the number of workmen, the provisions and wages. All this we find in Qin Zhoushao's work, at the same time as its advanced nature. In Qin's work all the basic operations are taken for granted. For a beginner's textbook its problems are much too complex, it would be useful only for advanced students. It is possible that they were unsuccessful substitutes for older books written in a less advanced phase of mathematical knowledge. But as mentioned earlier, none of the writers was a mathematics teacher. Even Li Yi's work, which was printed in the 13th century, was never used as a textbook. What can be said at the moment is that the work of the Song mathematicians, for the student who is prepared to overcome some formidable initial obstacles, is a really promising field of research. While much progress has been made in understanding them, there are still controversial points and open questions. The mixture of practical setting with the pursuit of difficulty apparently for its own sake, while not unique to the Chinese, could lead us to think again about what mathematics is for. Exercise 5. Find the equation which solves Li's problem, and check that x equals 240 is a root. A note on equations. At various points in earlier history, it has been necessary to exercise caution about using the word equation for the activities of the Babylonian scribes, for Euclid's Book 2, and so on. Still more have we tried to emphasize that, if we write a Babylonian problem in terms of XS, it is to help us read it and not to indicate how the authors thought of it. If this caution is noticeably absent in those who write about the Song mathematicians, this is because what they wrote down does look remarkably like an equation, even if it has no x and no equals 0. To see this, look at Figure 7, which reproduces the equation for Chen's problem 6.2. We translate this as x plus 15,245 times 6,262,506.25 is equal to 0. The coefficients are written in a column from the constant term downwards. Below each one is its rank, a verbal symbolic description of the power of the unknown to which it belongs. Positive and negative coefficients are distinguished by writing the relevant word by them. It is not an equation as we know it, but it can be seen as a convenient translation of one to the language of arrays which had been so successful in the 9 chapters, and Chen's subsequent manipulations seem to be related to the Fangcheng method. No more an equation than an array is a matrix, it is a clearly defined tool of equivalent sophistication. Perhaps we should still be cautious about translating it into our own terms, but we hardly need a dictionary to do so. 8 on transfers, when, and how. Seek knowledge, even as far as China. Aside from the unusual nature of algebra in Song times, why was it being done, and what were its rules of operation? We have what is sometimes an open question, sometimes an argument about origins. Several apparently similar techniques, most particularly the use of the binomial triangle and of techniques for solving equations by approximation, seem to have appeared both in China and in the Near East around the same time, say the 11th to 12th centuries. We know of numerous contacts between China and the Islamic world, the earliest relevant one being the compiling of a calendar, a perennial headache for the government, by a Muslim named Ma'isa for the emperor in the late 10th century. From then on, Muslim scholars seem to have been frequent visitors, until under the Mongols of the Yuan dynasty a large number of Muslim artisans were settled in North China, and one Zamaluddin presented the Emperor Kublai with yet another calendar and astronomical instruments. Arabic or Persian astronomical and mathematical books were also imported. Given all this, it seems to make for historical economy to suppose that some transmission of knowledge was taking place one way or the other. However, as with the question of counting rods and the decimal system, it is more complicated than we might wish. For example, 1. There is no record of any mathematician of either culture referring to work from another. As Saidan notes, Almas Udi writes much about Hindu wisdom and learning, and refers to Chinese technology and social life, but never to Chinese science. The learned Al-Bir-I does not refer to Chinese science in his chronology, nor does Aid in his T-Abakat. 2. The essential works in which the Chinese methods were introduced, such as those of Jiaxian, are lost, and as Martzloff says, our knowledge of this subject is very imprecise, since it is based on extracts from 13th century works such as those of Yang Hui or Zhu Shijie, accessible to us through the medium of 19th century editions. 3. So far as we can draw a parallel between Chinese and Islamic algebra, they seem to have been very different pursuits. In non-Chinese algebraic manuals, this character is treated with the utmost care and respect. It is studied in minute detail, in the search for the secrets of the algebraic formulae which unveil the results. This initially involves a study of equations of degree 2, since these are the most docile. But in medieval China, the degree of equations is of little importance. Chinese equations are not exactly equations, but algebraic forms or schemes for extracting roots, which consist of sequences of numbers to be operated on, as though one were extracting square, cube or nth roots. Given this, and given the specialized technical language of Chinese algebra, it is not surprising that the question of what could have been transmitted is a hard one. Let us consider a practical problem which leads to an equation, from Shushu Jiuzhang, 3. 1. The problem is to find the area of a pointed field when one knows the measurements shown. Again, the answer could be found trivially, h equals 36, h equals 20 by Pythagoras, area equals 840. Again, one assumes that Qin knew the answer in setting up the problem, and, as in the preceding question, that he knew it could be solved easily. Instead, he A equals 39. A equals 39. B equals 25. C equals 30h. H. B equals 25. Figure 8. The pointed field, from Qin Zhouxiao's problem, takes the numbers A equals B equals. He then shows that the area satisfies the equation x plus 2x equals 0. In fact, x equals a plus b, which is a root of the equation. Feeding the numbers in, this equation becomes x plus 763,000 times 40,642,560,000 is equal to 0. In the Western world, which for our purposes at the time means Islam, the idea of applying such exotic methods to a simple problem would have been rejected out of hand. Equations involving only powers of x were known, and had been dealt with by the simple method of treating them as quadratics in the variable a square of thing, or x, but the Chinese notation with its negative signs would have posed difficulties. What Qin does, and this is again odd if we suppose that he knew the answer, is to embark on a sophisticated approximation procedure. This makes sense if you are trying to find 2 to 3 or more decimal places, but for x equals 840 it looks like overkill. The idea is to find the figures of the answer one at a time. If we know equals 0 becomes f equals 0. Qin's method is to use a simple way of working out the coefficients of y in the new polynomial g equals f, which he demonstrates by a sequence of rod number diagrams. The method which he used has been known since its rediscovery in the 19th century as the Ruffini-Horner procedure. It is now certain that some Chinese mathematicians and some Islamic ones knew and practiced this procedure, and the question of who might have borrowed from the other has become something of a crux in the question of what could have been transferred. It is not our intention to go further into the details of the procedure. See Martzloff, 1995, p. 232 ff and Librecht, 1973, p. 180 ff for the Chinese version and Rashid, 1994. p. 91 ff for the Islamic one. Still less are we about to discuss the priority, on which the evidence is slender to non-existent. A recent evaluation is given by Karine Kemla. It seems almost inconceivable, however little mingling there was between Chinese and Muslims at the Mongol court, that some knowledge was not shared, although it may have been at a fairly basic level. Given which, one might ask, why did Islamic mathematicians not learn anything of the matrix method, and the use of negative numbers as routinely practiced by the Chinese? Why did the Chinese not learn the formula for the volume of a sphere, the construction of the regular solids, and the properties of conics? The problem is as much to explain what was not transferred as to find what was. A different question arises in response to the argument that the occurrence of the same idea in two cultures must imply copying. We could then ask how difficult we think its discovery might be. Pascal's triangle is a case in point. At one level, it is a pattern of numbers which one could discover if one were playing with them idly. As Martzloff comments on Needham's assertion that it was transferred from China to India, what was the triangle, in a given culture, being used for? Ancient Indians used something like it for problems involving combinations, Pascal for probabilities. In Samarkand and Beijing it seems to have been more an aid towards root extraction, via the relation of the nth row in the triangle to the coefficients in But this is not so difficult that one has to suppose its discovery to have happened only once. Sometimes at an elementary level, the same ideas occur with the same. Figure 9 Pascal's triangle. Numbers as examples, then one can suppose that there is a common source, though there is usually not enough evidence to deduce what the ultimate source was. 9. The later period. The Ming Dynasty, 1368-1644, a Chinese dynasty which overthrew the Mongol rulers, saw a second period of a decline, in that while mathematical work was still done, the emphasis was on commenting the classics, and the innovations of the 11th to 14th centuries were gradually forgotten. The works were lost or found too difficult. Whether this was a result of the introduction of the abacus, as some writers have suggested, or because of a renewed value given to the literary as opposed to the practical arts, the description of the Song and Yuan as a golden age and of the Ming as a period of stagnation are a commonplace. This was dramatically changed by the arrival of the Jesuit missionary Matteo Ricci at the end of the 16th century. An able scientist himself, Ricci saw the key to conversion in the exploitation of Western science and technology, which were just entering the period we call the scientific revolution. Once again, the calendar was seen as a way in. We should change the Chinese calendar. This would enhance our reputation, the doors of China would be more open to us, our position would be more stable, and we would be freer. Besides constructing the new calendar, Ricci with his Chinese assistants translated Euclid and other Western works, simplifying as they went along. The Jesuits successfully predicted eclipses, which the old calendar had been failing to do, and introduced logarithms not long after they had appeared in Europe. The fall of the Ming and their replacement by new outsiders, the Manchu-Qing dynasty, did not basically interrupt this program? Was the result a victory of the new European methods over the classical Chinese? Emphatically not. The Jesuits hoped that the certainty of Euclid's geometry could be related to that of their religion. They were not the first nor the last to make the equation. Naturally, a reaction set in, and there was a revaluation of traditional Chinese mathematics, helped by scholars who rediscovered and edited many of the classics from the 17th to the 19th centuries. From this period date such fascinating hybrid of figures as May Wending. Euclid's geometry is completely transfigured in May Wending's three-dimensional figures, which take no account of perspective, and in his immersion in numerical computation 12. At the same time, May Wending rehabilitated ancient Chinese techniques such as the Fangqing method for solving linear systems. Again, there is much more work to be done on the history of Chinese mathematics after Ricci, precisely because it remained in tension between a vital, indeed increasingly strong tradition and the Western mainstream. The final victory assimilation to Western mathematics came, naturally, with the fall of the emperor in 1912. It has to be said that many other writers in the Middle East and in Europe had a transfigured Euclid's geometry in different ways by this time. Solutions to exercises. 1. We would probably call the original serial x. Then after the three taxes have been exacted, there is left x equals 1635x. Hence x equals 17,516 equals 101,516 do, and 1516 do equals 15016 sheng equals 9 sheng. The 9 chapters of course does not use hex, but proceeds inversely, telling you to multiply the remaining 5 by 3, 5, and 7 and divide by 2, 4, and 6. The result is the same. The 9 chapters solution is given above in section 4. We would call the number of contributors x and the price y, and arrive at simultaneous equations. 9 times 11 is equal to y. 6x plus 16 equals y. It is then usual to subtract, and get 3x equals 27, so x equals 9, from which y follows by substitution. 2. We have IB equals x. AY plus B equals x. From which, subtracting, y equals b plus b, note that a greater than a, because it gives the excess. Hence, y equals b plus b a. Here, b plus b is the divisor, and a is the lesser assumption. Substituting back, and simplifying, we gets equals of 1 plus a 1 b a. And now a b plus sub, the result of cross-multiplying, is the dividend. In this case, the dividend is 3 plus 4 is equal to 17, the divisor is 4 plus 3 is equal to 7, and the lesser assumption is equals. This gives 42 for the number of people and 17 for the price. 3. No solution required. 4. We have the matrix as simplified, and now we simplify it further. Following the Fongjing method, multiply the first column by 3 and subtract the third column. After which, you multiply the new first column by 5 and subtract for the second column. Result: 0, 0, 3 4, 5, 2 8, 1, 1 39 24 39. Five Islam, Neglect and Discovery. 1. Introduction. It should be clear from the present chapter that the traditional view of the Arabs as mere custodians of Greek learning and transmitters of knowledge is a partial and distorted one. A number of medieval thinkers and scientists living under Islamic rule, by no means all of them Muslims, either nominally or substantially, played a useful role of transmitting Greek, Hindu, and other pre-Islamic fruits of knowledge to Westerners. They contributed to making Aristotle known in Christian Europe. But in doing this, they were but transmitting what they themselves had received from non-Muslim sources. The history of Islamic mathematics is clearly a contested area, and recent history has if anything sharpened the divisions. The view which Joseph described as partial and distorted 13 years ago lives in some academic circles, as the quote from a admittedly right-wing anti-Islamic columnist illustrates. It is perhaps natural that in the current context even questions about algebra in Baghdad in the 9th century should be charged with political relevance, and voices on the fringe should perpetuate old myths. As far as the mainstream of historians is concerned, the points made by Joseph are almost universally conceded, as Katz's recent respected textbook makes clear. Islamic mathematicians fully developed the decimal place value number system to include decimal fractions, systematized the study of algebra and began to consider the relationship between algebra and geometry, brought the rules of combinatorics from India and reworked them into an abstract system. Studied and made advances on the major Greek geometrical treatises of Euclid, Archimedes, and Apollonius, and made significant improvements in plane and spherical trigonometry. The only quibble which could be made against this generous assessment is that Katz does not mention the difficulties which previous scholars have had in getting such reasonable claims accepted. The major obstacle has been the viewpoint, referred to by Joseph, which sees the Arabs as transmitters rather than innovators. Why is this? We saw in the last chapter that Chinese mathematics, obviously outside the Western tradition, could be relegated to the sidelines as a mere collection of isolated problems without coherence and without any idea of proof. With the mathematics which was developed in the Islamic world from the 9th to the 15th century CE, the problem is the opposite. The work could with some justice be seen as a part of a Western mathematics, looking back to the Greeks and forward to the European Renaissance, and the existence of influences is not in dispute. However, because it was a specialist field of study and the original texts were often inaccessible, it was possible to forget the ways in which the Islamic writers transformed mathematics and to claim that they did nothing but pass it on. Tounder taki proper discussion of the historicities no understood, itis useful to look briefly at the West, the Islamic world, and their changing interactions. The understanding of Islamic mathematics. In Western Europe has gone through a variety of transformations. In the early Middle Ages, from the 11th to 13th centuries, it was highly regarded, for the good reason that the level of achievement was visibly more sophisticated. Those works which were found most comprehensible or useful were translated from Arabic into Latin, as were the contemporaneous translations of the Greek classics into Arabic. By the Renaissance, for complex reasons, there had been a change of view, even though the West had not overall achieved the Islamic world's level of achievement, much less overtaken it. The practice of translation from Arabic was less frequent, while the publication of original Greek texts and their translation again into Latin, made possible a claim that the moderns were the direct inheritors of the ancients. Even though, as far as algebra and the number system were concerned, this was clearly untrue. It was mython constituting a Renaissance worldview which built on the classics as a source of legitimacy. We shall see later how much the work of Fichte, Stavine, Descartes, and their contemporaries owed to Islamic precursors. What is important for the moment is that it was not normal to acknowledge the debt. It is not excessively oversimplifying to say that they brought outline us off the Eurocentric history, which Joseph criticizes, were laid down in the 16th century, and were the dominant version of history until relatively recently. And yet a number of important, often striking Islamic works have been published and studied in Western Europe over the last 200 years. Their understanding, and their incorporation into a general history remained the preserve of specialists with no impact on the mainstream view. A better understanding of what Islamic mathematics was has had to wait for. 1. A political motivation, the demand for recognition from the Islamic world from the 1950s on. 2. Unified research programs, partly related to that politics, which rapidly deepened and expanded the work of study and translation in the 1950s and 1960s. We shall have more to say about what material is and is not available in Section 2. The important change has been not so much an increasing accessibility of sources as an increasing consciousness of the achievements of the Islamic mathematicians. 20 years ago, Rashdi Rashid, one of the leading historical researchers, made much the same points as Joseph. The same representation is encountered time and again. Classical science, both in its modernity and historicity, appears in the final count as the work of European humanity alone. Furthermore, it is essentially the means by which this branch of humanity is defined. In fact, only the scientific achievements of European humanity are the objects of history. New texts, new research, and persuasive arguments by respected scholars have largely allowed Islamic mathematics to take its legitimate place in the histories, and among scholars with any serious academic credentials one will no longer find it neglected or downgraded. The main problems in building up a proper picture are constituted first by the great gaps in our knowledge, which are, of course, also there for the cultures of Greece and China, and second by the sheer diversity of activity over. 1. This case is argued by Rashid. The general point is incontestable, although there is disagreement about the detail. 2. Said's influential book, although quite unrelated to the sciences, played a key part in making academics more self-conscious about how they treated things so oriental. 3. Rashid's book dates from 1984, although its English translation is 10 years later. What is once again a dauntingly long historical period. It should be easy for the student to approach Islamic mathematics, like Greek, without prejudice and make a fair evaluation. Assuming this possible, one could, if only to fix ideas, pose some questions. 1. Can one give a unified description of Islamic mathematics, given the length of time and space and the variety of fields covered? Indeed, should we even try to do so? 2. How would we evaluate that Islamic contribution to the development of mathematical thought? 2. On access to the literature. One would naturally like to recommend, as a follow-up to the general agreement on the importance of Islamic mathematics, that the student could consult texts and histories and examine, for example, the questions raised above. Unfortunately, this is not yet the case, and here an accusation of neglect can still be made, in that access to the relevant materials remains extremely difficult. If we start with secondary texts, that of Berggren is full, readable, and well-informed. It is, in our current situation, where any reader should start. Rashid's work is more specialist, aimed at the exposition of particular points in arithmetic and algebra. It is also expensive and less often stocked by libraries. And while Yashkovich's rather older text is fuller than either of these and contains much which they exclude, it is in French and long out of print. The situation for the student entering the field could be worse, but it is not very good. With regard to primary sources, what is available reflects a long and patchy history of translation by individual enthusiasts. The relevant section in Fauvel and Gray, though it contains some essential texts, is relatively brief, and while the works of Euclid, Archimedes, and other major Greek mathematicians can often be found in libraries and are reprinted, This is far from being true of the classics of the Islamic world. One initial problem is that there is no longer a canon of a few great writers, rather a large collection of texts whose differing contributions are still in process of assessment. More translation is now in progress, but there are major gaps. To take just a few examples. 1. The earliest, founding book on algebra which underlies all subsequent work is Al-Khw Arizamiz H. Izab al-Jabr wa al-Muqabala. This exists in a translation by F. Rosen, dated 1831. It has been reprinted by Olms, and is therefore in a better situation than most. 2. Much later, but equally important, is the Algebra of Omar Khayyam, dating from about 1070. This has been known about for a long time. While it was first translated in the 19th century by Woke, there is a more modern, English translation. 4. By an irony in the history of research schools, a large number of very interesting texts were translated into Russian by Yushkovich and his group in the 1950s and 1960s. Even for the readers, whoever they may be, for whom Russian is an easier option than Arabic, they are not accessible in most libraries. This, however, is long out of print and far from easy to find. Again, there are good extracts in Fauvel and Gray. 3. A more recent find is the startlingly innovative algebra text Al-Biyahir Fayel Jabr of Al-Samuel. This has been extensively discussed, and good summaries of what is said in some key passages concerned with sums of series and with polynomials are to be found both in Rashid and in Berggren. However, while there is a modern Arabic text dating from 1976 with introduction and some footnotes in French by Rashid, there is no translation, indeed there are no translated extracts. And the edition itself, published in Damascus, is not likely to be stocked outside specialist libraries. 4. Lastly, one of the most famous works, often referred to for its sophisticated calculations, in particular the use of decimal fractions, is Al-Khw's Miftah. Al-H. Izab, written in Samarkand in the 15th century. This has been known and studied for over a century. Besides several editions in Farsi, and a translation into Russian by B. A. Rosenfeld in 1956, there is a modern Arabic edition, published in Cairo in 1967, and again long out of print. I know of no English translation, or even of any plans for one, although again one can learn something of the work's unusual features from descriptions in Berggren. There is now some serious translation underway, and since the field is very large, it is bound to be selective. One could single out A.S. Satan's version of the Arithmetic of Al-Khw's, a fascinating work to which we shall return, and numerous translations into French by Rashid, notably the works of Shar Afld in Al-T. Usai, and of Ibn al-Haytham. These translators, being active researchers, will necessarily be selecting those authors of most interest to them, so that the act of editing and translating is often part of the construction of a personal canon, of what the translator considers major works. However, in the impoverished situation already described, any such work is invaluable. It could be argued that a serious research engagement with Islamic science should include the acquisition of the ability to read Arabic. This seems misconceived, insofar as the works concerned are considered as major historical texts. The time is past when the student was expected to be able to have the leisure to learn languages as part of a general liberal education, and while the specialist might need to read Euclid in Greek or the Principia in Latin, no one would expect it of the student on a history course. In any case, as already stated, modern Arabic editions are not easily available, and the deciphering of the difficult manuscripts which are still our primary sources is an advanced research skill comparable to reading Sumerian. If the major works of Islamic mathematicians deserve study on an equal footing with the classics of other times, then they should be equally accessible. Those who research Greek classics are in a fortunate position, in that critical editions and translations have been made available by scholars who considered it an essential part of their work. A commitment to fair treatment for the Islamic classics is now driving a similar effort as far as they are concerned. In a spirit of optimism, one could hope for a significant part of this vast literature, together with a variety of analytical histories, to be readable by students in 20 years' time. A good recent bibliography of sources and articles is by Richard Hogendick at Figure 1 ms, page from Al-K-I. And many of the out-of-print studies and articles of the past 100 years are being printed as part of the vast series, entitled Islamic Mathematics and Astronomy, by Fyut Sezgin. The persistent student can find a great deal of material, but it may involve finding a friendly librarian, and possibly some expense. 3.2 Texts. No curiosity that occurs, no strange method unheard of, no nice idea that is liked by them who hear it will be left out. These will be given and clearly explained, so that this book will contain everything the people inquire about. For indeed this arithmetic is often debated by people who inquire about its whys and hows. It is a characteristic of geometers that when you ask them a question on the division of figures or the multiplication of lines, they fall into confusion and need a long time to resolve it. As an introduction to the nature and variety of Islamic mathematics, let us consider two texts from around the same date. Both illustrate the problem of a practical mathematics, which is raised by the two quotes above. For symmetry, one is a book, in print in an English translation, by an almost unknown writer, the other an untranslated book by an author of whom a fair amount is known. The first, which is relatively easy to find, is the Arithmetic, or Kitab al-Fus. Al-Fi al-H is a Balhind I, written by Al-Aqlides I in Damascus in 951 CE. The book is one of the best sources on early arithmetic using the decimal Hinduist system, particularly since the earlier one written by the famous Al-Khw Arizm I has not survived in Arabic, and the various Latin translations seem all to have added and subtracted in different ways. On the other hand, while Al-Khw Arizm I was a notable scholar, nothing is known of Al-Aqlides I's life at all. The name, which means the Euclidean, may indicate learning, but apparently people got this nickname for writing copies of the elements for sale. However, Greek learning makes no appearance in Al-Aqlides I's text. It is long, detailed, and careful, and its world is that of street corner calculators in Damascus who needed to work quickly and accurately, and who found that the new number system was ideal for their purposes. It was a competitive world, again this may appear strange, and one in which the partisans of one method of calculation would attack another. So Al-Aqlides I defends his method, in phrases which are often quoted, as making it possible to carry out calculations among the distractions of street life. Most scribes will have to use it because it is easy, quick, and needs little precaution, little time to get the answer, and little keeping of the heart busy with the working that he has to see between his hands, to the extent that if he talks, he will not spoil his work. And if he leaves it and busies himself with something else, when he turns back to it he will find the same and thus proceed, saving the trouble of memorizing it and keeping his heart busy with it. The book is outstanding in its immediacy, and in the sense that Al-Aqlides I has of his audience and what they need. Every rule is explained in great detail. For example, we try to find the root of 576. We start from the 6 saying is not, is, which falls under the 5. We seek a number to draw under the 5 so that if we multiply it by its like, it exhausts most of the 5. We find it 2. We insert it under the 5, multiply it by its like and cast that out of the 5. There remains 1 in place of 5. We double the 2 in its place, shift the 4 under the 7, and seek a number to draw under the 6 so that if we multiply it by the 4 and by itself it will exhaust what is above it. We find it 4. We multiply 4 by 4, get 16, cast that out from above. We multiply 4 by itself and drop that from above, nothing remains. We have the 4 which we have doubled. The result is 24. Clearly from the above, intelligence, numerical ability, and skill in following instructions are assumed, and there is no concession to a literary style once the initial points in defense of the book have been made. However, Al-Aqlides I does take the trouble to explain his rules where he thinks it necessary. Why repeat is not, is to know where to start in root extraction. Why double the extracted root before shifting? These questions are answered in Book 3, Chapter 6 Queries on Roots. The book is in no way an advanced theorem, proof Greek text, but it makes no pretense to being that. It is a completely practical text on how to do arithmetic with Indian numbers, and the shadowy Al-Aqlides I understands exactly what is required of such a book. We do not even know whether his text was popular, no other writers refer to it, and it seems to have survived by chance. There is a great contrast in the comprehensive geometric text written about the same time in Egypt by Abu al-Waf, al-Buzdani, entitled Kitab f-Imayah. T-Aju alayhi al-S da Animan am al-Handasa. This has to date only been published in Arabic and Russian. It is therefore not a text easily available to the reader, but it has been considered important by Yushkevich and Hoyrup and Berggren. We have done our best with the Russian text. Abu al-Waf was at the other end of the scale from al-Aqlidis I, a court mathematician and astronomer working in Baghdad who wrote commentaries on the classical works of Euclid and Diophantus, and numerous other works on mathematics, astronomy, and other sciences. That he thought it useful to devote time to writing textbooks for artisans is the more significant. As Ibn Khaldun says, in the passage which immediately precedes the story of Euclid as geometer. In view of its origin, carpentry needs a great deal of geometry of all kinds. It requires either a general or a specialized knowledge of proportion and measurement, in order to bring the forms from potentiality to actuality in the proper manner, and for the knowledge of proportions one must have recourse to the geometric aeon. However, while the world of calculators who might have used al-Aqlidis I's book is fairly easy to imagine from his text, the artisans who needed the book on geometric constructions seem more enigmatic. It is clear that Abu al-Waf had in mind an actual audience, but he wished to raise the level. Ethids and problems of Greek geometry and Abu al-Waf's own mathematical ingenuity are used to improve upon practitioners' methods, but the practitioner's perspective is also kept in mind as a corrective to otherworldly theorizing. Interesting passages include Chapter 1, on the instruments of construction, and 10.9 and 10.13, which discuss the failures of the artisans as well as the shortcomings of the geometers. Indeed, the quote which opens this section is just such a criticism of geometers. As an example of Abu al-Waf's method, here is the very classical construction of a regular pentagon. If someone asks how to construct on the line AB a regular pentagon, then we raise from point B a perpendicular BC equal to the line AB. We divide AB in half at the point D, we describe with D as center and radius DC the arc CE, and we extend the line AB to the point E. Then we draw arcs with each of the points A, B as centers and with radius equal to AE. They meet at the point G. We join the lines AG and BG. We have the triangle ABG, which is the triangle of the pentagon. From this point on, the construction is easy. AGB is an isosceles triangle whose base angles are 72, and the isosceles triangles BFG and AHG which complete the pentagon have their short sides equal to AB. There is, as Hoyrup remarks, no proof, and the G. Figure 2 Abu al-Waf's construction of the regular pentagon. Greek, we, is mixed with the artisans if someone asks you. Do. And one wonders how often artisans might have needed to construct a regular pentagon. There is an evident wish to publicize Greek geometry and to extend its audience, as al-Aqlidis I wishes to make propaganda for the Hindu numbers. Real mathematics, expounded systematically in books, has suddenly entered a realm of popularization for practical men. Exercise 1. Explain al-Aqlidis I's calculation. Why does one say A is not, is? Exercise 2. Justify Abu al-Waf's construction. For the Golden Age. The most venerable legal scholar Abu Bakr ibn Ahmad al-Yafrash told me in Zab ID the following story. It is related that a group of people from Frs with a knowledge of algebra arrived during the caliphate of Umar ibn al-Khattab. Ali ibn Abi Talib, may God be pleased with him, suggested to Umar that a payment from the treasury be made to them, and that they should teach the people, and Umar consented to that. It is related that Ali, may God be pleased with him, learned the algebra they knew in 5 days. Thereafter the people transmitted this knowledge orally without it being recorded in any book until the caliphate reached Al-Ma'mun, and the knowledge of algebra had become extinguished among the people. Al-Ma'mun was informed of this and he made inquiries after someone who had experience in. The only person who had experience was the Sheikh Abu Bakr Ahmed ibn Musa al-Khw Arizami, so al-Mamun asked him to write a book on algebra, to restore what had been lost of. The above apocryphal story of the arrival of algebra links the beginning of Islam with the beginning of mathematical knowledge among the Arabs. Significantly, however, it also introduces a group of people from FRs who are responsible for its introduction, and it illustrates our ignorance of the first century of Islam, particularly in drawing attention to the oral tradition and the lack of writing. All other evidence which we have tells a different story. While the origins of Greek and Chinese mathematics are unclear and undocumented, Islamic mathematics begins. 5. From the ease with which Ali learns algebra, the story appears to be Shurite in origin, but Brenches gives no further information on this. 150 years later, with an abundance of written texts from the 9th century CE, many of which have survived. As with Chinese history, Islamic history can be structured by a succession of dynasties. However, after the earliest years this becomes confusing and it is simpler to give a broad outline. In fact, the world which was quickly conquered by the forces of Islam was large, and it hardly ever came under an undisputed single ruler. The conquest by those who accepted Muhammad's new religion and message of Islam is one of the most spectacular events of history, however interpreted, between Muhammad's death in 632 CE and the end of the 7th century. The whole of the Middle East, Egypt, North Africa, Spain, Iran, and parts of India and Central Asia were incorporated into the new state, under the rule of the Caliph, first at Damascus and then at Baghdad. In the Orthodox history of Islam, the period of Umar and Ali, the companions of Muhammad mentioned above, was the Golden Age. Subsequent rulers, as always, fell off both in personal ethics and in their human rights record from the original standards, and the rulers who were remembered as good were those who at least presided over a period of peace and promoted the arts and sciences. In this respect, the Abbasid rulers of the early 9th century, particularly the Caliph al-Ma'mun, were outstanding. Indeed, the history of Islamic mathematics, like Chinese, seems to divide naturally into two periods, an early one of quite concentrated activity, with a large number of mathematicians, working often in collaboration, and a later one of particular scholars, often very gifted, who, in times often of civil war or external attack, worked either in isolation or under the patronage of local rulers. There are signs that as early as the 11th century Al-Biruni and Khayyam were looking back at the previous age, and contrasting it with their own. We have been suffering from a dearth of men of science, possessing only a group as few in number as its hardships have been many, persons who had recourse merely to a brief respite of time to concentrate on research and verification of facts. Most of our contemporaries are pseudoscientists who mingle truth with falsehood. In all circumstances we seek refuge in God, the Helper. Accordingly, when there was a revival, as in the Mongol court of the conqueror Hulagu Khan, or that of Timur's grandson Ulugh Beg at Samarkand, scholars looked back to the period of Al-Ma'mun and his House of Wisdom at Baghdad as a model. What was this golden age, and where did it come from? Early Islam was, as is well known, tolerant particularly to Jews and Christians, and it is thought that much of the population of this empire were slow in acquiring the Arabic language and the Islamic religion, although both had advantages. Similarly, in the first 100 years, the conquerors seem to have been unconcerned with the remnants of Greek learning, which were cultivated by scholars, often refugees from Christian persecution, in centers like Harran in Turkey and Jundashapur in Iran. The stage was set for a surprising union of cultures which took place in the late 8th and early 9th centuries. This was incidentally the period in which the religion of Islam took on most of its later form, the traditions with their injunctions about life and conduct, the legal system, and much else. The new Abbasid dynasty who ruled from Baghdad not only favored trade, commerce, and public works, but, particularly under al-Ma'mun, saw a value in pure research. In the context, this meant the discovery of the work of the Greek and Indian mathematicians, and its translation into Arabic. Scholars from what we can see as a melting pot, Syriac, Greek and Arabic speakers, Christian, pagan, and Muslim, combined in the work of translation, and then immediately began to build on what they had translated. In fact, With such disparate sources, the idea that the Islamic work could be simple borrowing and transmission makes no sense. A synthesis was essential. This involved raising what appeared to be unanswered questions, and writing new books in more useful forms for practical ends. In an article which we have already cited, which forms one of the most interesting theoretical discussions of early Islamic mathematics, Hoyrup claims that this new synthesis marked a radical change in the use of mathematics, comparable to the work of the Greeks discussed in Chapter 2. The break took place earlier, in the Islamic Middle Ages, which first came to regard it as a fundamental epistemological premise that problems of social and technological practice can lead to scientific investigation, and that scientific investigation can be applied in practice. Alongside the Greek miracle, we shall hence have to reckon an Islamic miracle. You are referred to Hoyrup's article both for his detailed arguments in establishing the nature of the new approach, and for his attempts to account for its origins. He considers and rejects a number of suggestions, finally opting for a description of the nature of Islam which he calls practical fundamentalism. We shall return to the role of Islam as religion, philosophy, and way of life later. Let us now look at the interaction between new and old in the knowledge produced by the early mathematicians. 5. Algebra, the origins. I have established, in my second book, proof of the authority and precedent in algebra and al-Muqabala of Ma. Ahmad ibn Ms al-Khw Arizmi, and I have answered that impetuous man Ibn Barza on his attribution to Abd al-H. Amid whom he said was his grandfather. I have always been very anxious to investigate all types of theorems and to distinguish those that can be solved in each species, giving proofs for my distinctions, because I know how urgently this is needed in the solution of difficult problems. The word, in its derivation, suggests that what we call algebra begins with the Arabs. Like all other questions of origins, this can be disputed on various grounds. We have seen that the Babylonians knew how to solve problems which were equivalent to quadratic equations. So what was so important and influential about the Islamic contribution? There is no better place to start than the original textbook by al-Khw Arizmi. This was enormously influential both in the Islamic world and in medieval Europe. Abu Kamil, as quoted above, illustrates the general agreement about al-Khw Arizmi's priority, and his method and language survived with adaptations until the 16th century in Europe, when something more like our modern notation was introduced. Part of the text of his book is reproduced in Appendix A. This illustrates the core of the book, the treatment of quadratic equations, although a very large part is in fact given over to applications, to practical situations, and to geometry. He defines the roots, squares, and numbers, the three objects which enter into his algebra, in terms of what you will do with them. The definition is not so much conceptual as operational, and this itself throws light on how he is thinking. A root is any quantity which is to be multiplied by itself, consisting of units, or numbers ascending, or fractions descending. This may seem less than clear to us, but it enables a description, the first, of what a general quadratic equation is. Note that the root, or solution, is allowed to be a fraction although not worse. You will still find this language, stretched to its limits, used in Tartaglia's rule for solving the cubic in the 1540s. There are 6 forms of the quadratic equation. This is dictated by the need for all numbers which are used to be positive. A typical one reads, roots and squares equal to numbers, some xs added to some xs equals some number. Al-Khw Arizmi does not wish, like the Babylonians, to list particular cases and assume that you can deduce the general rule. He wants his statement to be general. But he does not have our version of a general symbolic language, a roots plus b squares equals c numbers. If, in a parenthesis, consider how an Aristotle solves a chain equation today, the commonest method is to give a simple literal formula, whether it is proved or not. Writing the equation x plus bx equals c, we deduce x equals a plus or minus a plus 4bc2b, which always applies. The reason we can do this is because we can explain how to deal with several problems raised by the formula. First, one or both of the values we find may be negative numbers. which were first considered as possible solutions in India by Bhaskara in the 11th century, and were still being argued about 400 years later, as we have seen this was found easy by the Chinese. But their attitude seems not to have been transmitted to the West. Second, we have to be prepared to take the square root of any number we like. This raises two levels of problems, a naming a problem if the number is positive but not a square, which we shall see dealt with below, and a worse one, what are we talking about at all, if it is negative? These were coped with at different times in more or less satisfactory ways, and a school mathematics course will similarly try to steer the student through them progressively. Until the 16th century or later, though, no such general formula was considered, since even negative roots had to be dealt with separately if they were allowed at all. Hence the pattern which Al-Khw I set for dealing with equations case by case, as set out above. After describing the different cases, he moves on to the case roots and squares equal to numbers mentioned above, and deals with the problem of abstraction by alternating the general statement with its application to the particular example. 1 square and 10 roots equal to 39 direms. The solution goes back to Babylon, but has suddenly become general as well as particular. It is easy to see the reasons for the long popularity of Al-Khw I's text. He has grasped the idea of explaining the method through an example, as Al-Khw I was to do in his arithmetic. 6. Note also that despite Al-Khw I's role in introducing Indian numbers, they are not used in the algebra text, where numbers are always written out as words. 7. Why direms, a unit of currency? As one might say, x plus 10x equals 39 euros. The implication is that there is a practical use for the sum, and there is some attempt to justify this later. A B A B C E D F. Figure 3 Al-Khw I's first picture for the quadratic equation. It is necessary, he continues, that we should demonstrate geometrically the truth of the same problems which we have explained in numbers. Why is it necessary? There appear to be three requirements for the author. 1. To state what to do in general. 2. To illustrate it in particular. 3. To prove that it works. Is it the weight of the Greek heritage which implies that a proof means geometry? One might suppose so, since the Greek texts were being translated when Al-Khw I wrote. In any case, the geometry looks nothing like Euclid, or even his more practically minded followers such as Heron. The picture compared with later proofs of the same method is completely transparent. It is a good exercise to follow the proof through and see how verbal explanation and picture connect to give a convincing account of why the solution is the right one. There has been considerable discussion of how good a mathematician Al-Khw I was. As already stated, the method which he set out was ancient, wherever he derived it, and his exposition, his examples, and his proof were at a fairly low mathematical level. However, this seems to miss an important point. Such arguments assume that mathematicians deserve study only insofar as the work which they do is hard, while often this is not at all the case. What Al-Khw I did was to introduce a new way of thinking about the problem which brought together solution and proof, in a major synthesis, involving both generalization and simplification. That the mathematics involved was not very difficult was an essential reason for the method's survival more or less unchanged over the next 600 years. About 50 years later, Ibn Qura, who by general agreement was an able and interesting mathematician, wrote a text on quadratic equations. In contrast to Al-Khw I's treatise, it is a mere 6 pages. It was translated into German during the Second World War, and later into Russian. Figure 4 the diagram for Euclid proposition 2.6. The line AB is bisected at C, and BD is added. If now AK equals BD, then the rectangle AD by DB means the area of the rectangle ADMK, and this, together with the square on CB, is said to be equal to the square CEFD on CD. The proof is fairly obvious. The chance of finding either translation in a library is slim. However, it is a very interesting document. Th. was one of the groups of Greek translators, and much of his prolific work expanded on Greek texts, commenting or dealing with problems which they raised. Here he uses his knowledge to draw on Euclid's proposition 2.6 and prove, in some sense, that the formula is the right one. Unfortunately, unlike Al-Khw Arizmi, he does not have an easy style, at least here. Proposition 2.6, in its particular form, says: let the straight line AB be bisected at the point C, and let a straight line BD be added to it in a straight line. I say that the rectangle AD by DB together with the square on CB equals the square on CD. Those who believe that the results of Book 2 should be interpreted as a form of algebra interpret this by saying, call A beta and BD B, then BC equals a 2, and CD equals B plus. The proposition says that B plus equals. It is now on the whole thought unhistorical to claim that Euclid was thinking in such terms. However, there is evidence that the Islamic translators of Euclid at some stage did come to use some sort of algebraic translation. After all, they now had algebra to help them. In the early 10th century, the philosopher Al-Farabi wrote that the rational numbers correspond to the rational quantities, and the irrational numbers to the irrational quantities. The distinction between numbers and lengths, which sometimes seemed so important to the Greeks, was being eroded, and in commentaries by Arabic writers on Euclid's books V and X we can find many similar examples. Th. does say that he is investigating the case square and roots equal to numbers, but it is typical of his more hurried and more abstract approach that he gives no numbers as examples. You can find his argument in Appendix B. The end result is that the root which we are looking for is known. In classical geometric terms, it can be constructed. What Th. does next is equally interesting. He goes through his method and shows, stage by stage, that it is the same as the method used in algebra. The algebra is the method described by Al-Khw Arizmi without his geometric proof, and it seems reasonable on various grounds to suppose that it is precisely his book which is referred to. This dialogue casts some light on different ways of thinking about geometry, numbers, and algebra in the earliest period of Islamic mathematics. It would seem that Th. is saying, anything which you can do by algebra, I can do by Euclid Book 2. If so, there is some misunderstanding both of Al-Khw Arizmi's algebra and of Euclid. More positively, we could see it as an attempt to harmonize the down-to-earth practice of algebra with Greek theory. Whether misunderstanding or harmonization, such a tension between theory and practice was to be of immense value in the further development of the Islamic tradition. We have already entered the domain of conjecture about what the text means, in terms of the various ways 10th century mathematicians thought about numbers and geometry. The problem is what Th. means by his known, the argument being that to say that the side is known is to solve the quadratic equation. There are two competing interpretations of this. In geometric terms, it means simply that the line which represents the side can be constructed, which is certainly true. But what has been passed over is the numerical question of what happens when your answer is not a whole number, as it was in Al-Khw Arizmi's version. If the equation is square and 2 roots equal 1, then the answer, whichever method you use to arrive at it, is 2 1. Because Th. is avoiding using numerical examples, he gives us no idea about whether such numbers are allowed as numbers, not as geometrically constructed lines. They have no name. There is a useful word for having no name in Arabic, which was variously applied. It is asdam or adef. This was initially applied to certain fractions. You can say the fractions up to 1/10 using one word, but after that you have to use phrases like 1 part of 13, and such fractions were asdam. But in Al-Khw's arithmetic, the same word was applied to squares which have no roots. By extension it denoted their inexpressible roots. This word translated, when the Arabic arithmetics were put into the Latin word for adef, cerdus, used in the form of surd as recently as 50 years ago to refer to roots like 5. At some point a linguistic concept about numbers whose names you could speak translated into a way round their unspeakability. They are still numbers, but numbers which need phrases rather than a single word to express them. Al-Euclides I devoted some space to finding approximations for such square roots, in chapters which follow on the exact root extraction quoted above. His formulae were not new, but the use of Indian numbers makes the procedure more transparent. Exercise 3. What kinds of combination of roots, squares, and numbers make an allowable equation, in the terms set out by alkhw I? Exercise 4. Why is the algebraic formula given equivalent to Euclid's proposition 2.6? Exercise 5. How would alkhw I's method and th construction approach the equation? Square and 2 roots equal to 1? 6. Algebra, the next steps. We have heard the great Eastern mathematicians have extended the algebraic operations beyond the 6 types, and brought them up to more than 20. For all of them they discovered solutions based on solid geometrical proofs. God gives in addition to the creatures whatever he wishes to give to them. Not much later than Th Abit's text, the Egyptian Abu Kamil wrote what is commonly considered the second generation algebra after that of Alkhw I. The work of Alkhw I is explicitly referred to, and many of the examples are the same, but much else has changed. The simple geometrical diagram has been replaced by a reference to Euclid's Book 2, but with numbers included. For the first time, as far as we know, numbers have been introduced into Euclidean propositions as a matter of routine, and proposition 2. 6 is being interpreted more in the algebraic sense referred to above. If this was done by the ancient Greeks, or by any of their successors, they were much more discreet about it than Abu Kamil. However, what Abu Kamil did next was even bolder, as an innovation. Again, it may arise from the study of Euclid, in this case of his Book X, but this is not made clear, and the language is completely different. He develops a set of rules, not complete, but useful, for calculating with roots, and uses them freely in many of his examples as if they were numbers. The result is an enormous expansion of the collection of equations you can solve, and of numbers you can name. Oddly, this appears not so much in dealing with whole number examples leading to square root solutions, as with examples where roots are part of the data of the problem. Here is the brief, but quite a hard problem 39. If one says that 10 is added to an amount, and the amount is multiplied by the root of 5, then one gets the product of the amount by itself. For the solution, make the amount a thing and add 10 to it to give 10 plus a thing. Multiply by the root of 5 to give the root of 500 plus the root of 5 squares equal to 1 square. Have the root of 5 squares to give the root of 1 1/4. The root of the sum of the root of 500 plus 1 1/4, plus the root of 1 1/4, equals the amount. Notice that though the problem deals with numbers like 5, they are still expressed in words, there is no notation for them, and there will not be one for a long time. For us, Abu Kamil's problem needs a considerable amount of unpacking. In modern terms, setting x for the amount, it is 5 equals x. This Abu Kamil solves by our usual prescriptions for quadratic equations again. In a slightly roundabout way, he changes the left-hand side into 500 plus 5x. He halves 5 to give 1, and arrives at the answer x equals 500 plus 11/4 plus 11/4. All these numbers are still expressed in words, as is done in the above quote. The formula, if you like, is exactly the same as had been used by Alkhw I, but the way in which it is applied has. 9. This can be found in Levy's translation of Mordecai Finzi's medieval Hebrew version, again not easily. There is an extract in Fauvel and Gray 6.b.2. And a very interesting and complicated equation is discussed in Berggren, page 110, 111. Been vastly extended, without this ever being made explicit. The earlier author never said that numbers could not be square roots, and the later one never said that they could, but all the same the idea of what numbers are allowed has changed. It is easy, in the fairly open climate of discussion in Islamic mathematics, to find differences of approach such as those described above, and they are not confined to algebra. There are explicit arguments, for example, about the merits of those who were already being called the ancients. said how much he appreciated the book, which he considered of great value, although he regretted that the author followed the way of the ancients in their use of the cutting diagram and of compound ratios. He said that he had obtained, to determine the azimuth, elegant methods which were more concise and better. However, to use this particular quarrel, or any other to divide Islamic mathematicians into schools, as has sometimes been done, seems premature, and probably misguided. Saidan in his introduction to Al-Uqaides calls attention to attempts of earlier historians to distinguish those mathematicians who used Indian numbers from those who used sexagesimals, and points out that it was common, especially in teaching texts, to use both, since the student might need both. As for Greek authority, it was universally recognized, and used as and when necessary together with more modern methods. The case of Omar Khayyam is particularly worth considering. In his algebra, he considers in detail the case of cubic equations. He was the Eastern mathematician, referred to by Ibn Khaldun, who had brought the number of types to more than 20 by introducing the various types of cubics. Besides being the natural next step after the well-understood quadratics, these had arisen in a number of special problems which he lists: a problem of Archimedes on cutting the sphere, trigonometric problems such as finding sin 10 given that one knows sin 30, and so on. As has often been noted, he acknowledges that it would be desirable to find a solution in terms of a numerical procedure, as had been done for quadratics and as Tartaglia and Cardano were to do in the 16th century. When, however, the object of the problem is an absolute number, neither we, nor any of those who are concerned with algebra, have been able to prove this equation. Perhaps others who follow us will be able to fill the gap, except when it contains only the 3 first degrees, namely, the number, the thing, and the square. Unable to achieve this, he followed the very Greek practice of drawing intersecting conic sections, just as Menaechmus had done for the simplest case x equals 2. 10. On the whole, such a solution would have been acceptable to a Greek. Omar was in some ways particularly close to the Greek geometers in his outlook. He criticized Ibn al-Haytham for using motion to prove the parallel postulate, and the algebraists in general for using the ungeometrical powers of the unknown above the third. However, it may have occurred to him to ask a question which fits much better into the framework of the algebra we have been discussing above, namely, if you have constructed a solution geometrically, what kind of a number have you found, and what can you do with it? There is a clue when, in a different work, he considered the difficulties in Euclid's theory of ratios. 10. For an extract from Omar's work, see Fauvel and Gray. He came to a startlingly pragmatic conclusion. We should think, he says, of a quantity not as a line, a surface, a volume or a time, but as a quantity which the mind abstracts from everything, and which belongs to numbers, but not to absolute and true numbers, for the ratio of A to B may often not be numerically measurable. That is to say, one may not be able to find two numbers whose ratio it is. This is how calculators and surveyors proceed when they speak of a half or other fraction of a supposedly indivisible unit, or of a root of 5 or 10, etc. In other words, the calculators and surveyors are already using numbers on the assumption that they are the same as the quantities, that if you can construct a length, there is a number which corresponds to it. What is interesting is Omar's explicit suggestion that mathematicians could learn something from them. Exercise 6. Show that the equation given is equivalent to Abu Kamil's problem, and solve the equation. Exercise 7. Use the formula sin equals 3 sin x for sin x to find a cubic equation for sin 10. 7. Al-Samoal and Al-K-I. The Calculator's Key is an excellent guide to elementary mathematics, written to answer to the needs of a large public. Considering the richness of its subject matter and the clarity and elegance of its presentation, this work holds an almost unique place in the whole literature of the Middle Ages. It would take much more space to discuss all the varieties of mathematical practice which were undertaken in the Islamic world, their connections and interrelations, although we shall return briefly to their views on Euclid in Chapter 8. However, in a specific attempt to investigate the themes of innovation, tradition, and continuity, let us consider two later mathematicians whose approach was very different, Al-Samoal and Al-K-I. In both cases, there are acknowledgments of particular influences. Neither is working in what we have called the Greek tradition, and both raise interesting unsolved problems about the aim and scope of their work. In particular, both present examples of what we might call excess, that is, calculation beyond what is necessary or useful, and here we would differ from Yushkovich's opinion above, with his references to elementary mathematics and a large public. In contrast to Al-Uqaidisai or Abu al-Wafai, they seem to be carried away by their subject. Why? Al-Samu'al appears the more straightforward case. His major work, of those which survive, is Al-Biyahir fi al-Jabr. Written, it is said, when he was 19, it is a conscious attempt to strengthen and deepen the results of his predecessor Al-Kharajai a century earlier. The work is quite long and contains a variety of results, but it is most celebrated for the curious study of polynomials in which 1. The primary aim is not to find the thing, it seems, in the main, to be treated as an abstract entity to be manipulated. 2. The powers of the thing considered are not only positive but negative, what we would call 1x, 1x. Figure 5 table from Al-Samu'al. In Al-Samu'al's famous phrase, from his introduction, his aim is to proceed by operating on the unknowns by using all the arithmetical tools which the arithmetician uses to operate on known numbers. In other words, you must, at least, be able to add, subtract, multiply, and divide your things any number of times. This leads to expressions which are complicated in our terms, let alone in 12th century notation, where 1x is designated by a part of thing, and so on. Al-Samu'al wastes no time. By his 4th page he is giving a table of powers of the thing up to the 9th, which we would call x, and he calls cube in the positive direction, and down to 1x, or part of cube in the negative. The table is an interesting mixture of notations. While the second row describes the powers in words, the first row keeps track in a more rational way by using numbers going in both directions, including 0. Underneath he gives the examples of powers, positive and negative, for the numbers 2 and 3. And here another notational problem, while the Indian numbers do very well to express 2, 4, 8. 2 is equal to 512, the corresponding fractions have to be written in words starting with half, and ending with an eighth of an eighth of an eighth. The power 0 is correctly assigned to 1. One has a sense, in the chapter on polynomials which follows, that Al-Samu'al is working at the limits of the notational possibilities which were then available, and trying to expand them where he can. Sometimes an example equals plus is set out and explained in words. Sometimes a more general formula equals b is described by using a series of Arabic letters A, B, C to denote the unknowns and the results of multiplying and dividing them. This in itself is not new. The use of letters to denote general numbers or quantities can be paralleled in Euclid, but in combination with the traditional algebraic language it gives the feeling that we have something near to a new, abstract algebra. The real coup is achieved when, after another 24 pages, Al-Samu'al sets out to divide two expressions according to the schema shown in Fig. 6. Before the table is set up, the problem is set out in words. Translated into our notation, it amounts to dividing 20x plus 2x plus 58x plus 75x plus 125x plus 96x plus 94 plus 140x plus 50x plus 90x plus 20x. Figure 6 table from Al-Samu'al showing division by 2x plus 5x plus 5 plus. This is far from being the hardest such sum which will be tackled, in particular. 1. All the signs are positive. 2. The division has an exact result. At this point the simple-minded reader might reasonably ask, what on earth did Al-Samu'al have in mind? The calculations which he undertook seem to be an end in themselves, a display of technical virtuosity on a theme which could have had no practical application, and which led nowhere. The example shown above, by the way, is by no means the end of the story. Later, a division by 6 squares and 12 units has no exact result. He therefore simply continues as far as possible, noting finally that any future coefficient can be determined by a formula. He is clearly on his way to understanding a particular form of infinite series. The calculation is discussed in Berggren 1986, pp. 117-18, who the audience of his book could have been, and what they made of his work, remains at present a mystery. No subsequent algebraist refers to it. And on the face of it, such preoccupations give the lie to any easy characterization of Islamic mathematics as practical or down-to-earth. A clue could be provided by a still more obscure work of al-Samoal, his recently discovered unpublished arithmetic. This is discussed at some length by Rashid, where an extract is provided, with a promise of future publication of the whole. In this text, according to Rashid, al-Samoal effectively introduced decimal fractions, using a schema very much like the one in Fig. 6, with ascending and descending powers of 10 taking the place of the powers of the unknown thing. This of course has a much more useful appearance from our present-day viewpoint. Although as Rashid concedes, by writing the numbers in a table al-Samoal had not yet arrived at a simple and efficient notation. Once the phrase of decimal fractions is mentioned, we have to deal with a long-running controversy over who was their originator. The question is interesting, but not because it really matters much anymore. In textbooks from the 1950s or before, it was claimed that the invention was due to Simon Stevine, despite the fact that Al-Ashai's much earlier calculator's key, which used them extensively, was already known widely enough. There was no obvious line of influence from Al-Ashai to Stevine, and Stevine's was the first European discovery. It followed that he was the inventor. Besides the obvious Eurocentrism of such a judgment, and the increasing evidence that Al-Ashai's work did influence Western Europe via Constantinople and Venice. 11. This illustrates the whole problem of how one ascribes priority. The main interest in a mathematics textbook is to explain how you use a technique, not where the author obtained it. And this seems true even of Islamic writers who worked in a culture where citation of sources could be quite careful. Hence even where work is original, such originality may not be claimed. And this leaves the field wide open for historians to argue about who is copying whom, and whether a writer really understands the method he is explaining. Al-Ashai certainly did know what decimal fractions were, he has a technical term for them, and uses them simply and with facility. In some sense, his introduction of them seems to be a claim to their invention, allowing that one does not always know who may have preceded one. We divided the unit into 10 parts, we then divided each tenth into 10 parts, and then each of them into a further 10 parts, and then each of them into a further 10 parts and so on, the first division being into tenths. And in the same way the second into decimal seconds, and the third into decimal thirds, and so on, so that the orders of decimal fractions and wholes are in the same relation as is the principle in astronomical numbering. We call this a decimal fractions. From this stage in his book, Al-Ashai sets out his results, where possible, in both forms, both sexagesimal and decimal. Whether his work diffused to Stevine, whose notation was different and in some ways less user-friendly, is still unclear, though it appears increasingly a possibility. But before Al-Ashai, as Rashid pointed out, stands al-Samoal, who also can claim a place as inventor, and before him there appears the still earlier 10th century figure of Al-Aqlidis I, who seems to be using decimals in at least 2 places in his book. And in between these writers there may be many others of whom we know nothing. Rashid considers the claims of Al-Aqlidis I unacceptable. There is no sign that he was following a practice which he understood in a systematic way. On the other hand, he may have been one of a number of reckoners who had realized the obvious fact, as Al-Ashai states it, that, with Indian numbers as with sexagesimals, you could continue on the right as well as on the left, with your number having a smaller meaning the farther you went. This is what Al-Aqlidis I seems to be doing when, in one of his crucial passages, he performs a sequence of halvings on 19. For example, we want to have 19 5 times. We say, 1/2 of 9 is 4 1/2, we set the half as 5 before the 4, next, we have the 10. We mark the unit's place. That becomes 95. Now we have the 5 and the 9, we get 475. We have that and get 375, the unit's place being thousands to what is before it. For if we want to say what we have got, we say that having has led to 2 and 375 of 1000. A great deal of ink has been spilled over that single dash between the 2 and the 375. Is it a decimal point, and why are there no others, and did Euclides I understand the fact? A tentative conclusion might be that he did, to some extent, but that he would not dream of codifying the idea as I did 500 years later. He was a calculator, not a mathematician. Indeed, the illustration shows that the actual discovery of decimal fractions is not as much of a marvel as one might suppose. If you want to show your skill in Indian numbers by having repeatedly, then you fall upon them almost naturally. Having mentioned Euclides in the context of decimal fractions, let us note a broader appreciation of his work, and of the calculator's key in particular. In the long letter to his father published by Edward Kennedy in Al-Kashi gives a fascinating picture of the court of his patron Ulugh Beg. This may have been the end of Islamic mathematics as far as our official histories go, but the society is far from being in decline. The atmosphere is one in which a sizable and intensely competitive community of scholars strive to obtain the king's approval, primarily on the basis of their mathematical ability. Al-Kashi, how was not given TOEFL's modesty, makes it clear to his father that he has consistently come out best in all of these competitions, partly because of his skill in combining theory, calculating ability, and knowledge of the construction of instruments. It was for this unusually mathematically literate community of teachers and learners that Al-Kashi wrote the calculator's key, a very diverse collection of arithmetic, algebra, and geometry with results of the most various kinds. Unlike Al-Samuel's book, this became something of a bestseller. The British Library, which is not strong on mathematics, has 4 manuscripts, two from the 19th century. His same sir state at the outset, after a brief summary of his many achievements. Although some of these could not be discovered with the help of the 6 algebraic, yet in the course of this work I found numerous principles with whose help the groundwork of arithmetic is developed by the simplest means, on the easiest road, with the greatest profit and with the clearest exposition. I decided to write these principles and desired to clarify them so that they could be an instruction for others and a guide for the learned. Therefore, I have written this book and collected in it all which calculators may need, avoiding both the tedium of long-windedness and the excess of brevity. For the majority of methods I have drawn up tables, so as to simplify examination by the geometer. All the tables established in this book have been prepared by me, and to me belongs all that is sweet and bitter in them, with the exception of 7 tables. Indeed, the tables are a notable contribution to the work. We may already see a heavy dependence on the table for the exposition of complex calculations in Al-Samuel, but in Al-Kashi they are everywhere, as he admits. There are the standard tables, tables of currency conversion, of the properties of metals and other substances, tables of the areas of polygons, and more usefully, of different kinds of arches used in architecture. Almost always the numerical results are more accurate than they have any reason to be, and often they are given both in decimals and sexagesimals. As can be seen from the quote, Al-Kashi feels that they are an important contribution. He asserts his intellectual property in them, as well as an emotional relation. Most famously, beyond the static tables, we have the dynamic ones which show how you do a calculation. The reader is shown how to construct them, told in detail where to draw horizontal and vertical lines and make entries, so as to extract a root, and the often quoted example, in which he extracts the 5th root of 44,240,899,506,197 in decimals, can serve as a model. This example has been extensively discussed, in particular by Berggren. When he comes to doing the same and more in sexagesimals, it is more a summary. In our treatise entitled Treatise on the Circumference, we have found the roots of many numbers with many digits and adapted them in different ways. Anyone who wishes to know more can turn to this book. Furthermore, we present here an example of the extraction of a cube root and another example of the extraction of a subcube root. But, so as to avoid long-windedness in this book, we shall not here give an explanation of the process. It is easy for anyone who knows how to do it with Indian numbers, as it was explained in Book 1. At a certain point, we see, the tables, which are given, are a substitute for an explanation of the method. To see Al-Kashi's style of exposition in a different context, an extract from the geometrical section of the calculator's key, on the regular solids, is in Appendix C. with the inevitable table which sets out all the measurements you may possibly need for them. Clearly considered an outstanding mathematician by his circle and beyond, Al-Kashai still appears something of an enigma. Given the obvious high culture of his milieu, one would like more information on what preceded it and what followed. And one wonders how far the sometimes obsessive accuracy of his calculations is motivated by the demands of practice, by competition, or by a pleasure in the activity of calculating itself. Exercise 8. Look at the table for Al-Samuel's polynomial division, and try to follow through the progress of the division. Show that the result of the division is 10x plus 4x plus 10 plus plus. 8. The uses of religion. Islam provides a whole set of fundamental values. Among these values one finds the uniqueness of truth, the lack of contradiction between revelation and reason. These values, among others, have without the least doubt pushed forth research and have fostered the creation of open scientific communities. Allah is the ideal merchant. All is counted, everything reckoned. A more simply mathematical body of religion than this is difficult to imagine. Earlier in this chapter it was suggested that the argument for the importance of Islamic mathematics, indeed its centrality in a tradition which links Babylonians, Greeks, and moderns, is now established beyond argument. The idea that Islam itself played some role in the rapid development of the Abbasid period seems also undeniable. The question is, what was it? The argument that many or even most Muslim scientists were not Muslim at all is easily dismissed. Although a substantial number of important early figures belonged to tolerated non-Muslim religions, this had ceased to be true by about 1000 CE, and many leading mathematicians did more than simply conform, actively working in Islamic law or philosophy. If the Christians, Jews, and star worshippers of the Fertile Crescent had it in them to create a mathematical revolution, one might ask, why did they have to await the advent of a new religion and social organization to do so? We could simply accept a sociological explanation. But this does not explain the specific value put on learning, which led to the Greek and Indian inputs, or the ways in which it was put to use. We are unfortunately at some distance from 9th century Islam, which was in many ways still in a state of flux. Either Rashid's characterization of Islam as promoting reason, or Torrey's more materialistic view of it as a kind of accountancy have germs of truth, and both were argued in the early conflicts of schools. Was there no conflict between the Quran and pagan learning or philosophy? Had God decided everything and measured it from the beginning? Theologians discussed such points and competed for the favor of the caliphs. For example, is what can be known in Arabic, the language of the Islamic revelation, different from Greek science and philosophy in part because of its linguistic home? Or does there exist a universal logic of thought that transcends particular expressions in use in a given culture? The hadith, as yet one more category, already contain numerous admonitions about the value of knowledge, its reward, and the duty to seek it, to gather and preserve it, to journey abroad in search of it. 3. Page 101. The general question of the relation of Islam to pagan and/or practical knowledge is a large one, and we have neither the space nor the ability to deal with it adequately. However, 2 points should be made. 1. Islam did certainly differ from Christianity in the value placed on knowledge, as the quote above illustrates, and the language of the Quran itself is strongly centered on appeals to reason. The Quran is a holy book in which rationality plays a big part. In it, Allah is continually arguing and reasoning. 2. Hoyrup's point, cited in section 4, by the 9th century at least, Islam had become codified as a complete system of practice, organizing every sphere of human action, from which the needs not simply for knowledge in itself, but for knowledge to inform practice followed. Rashid's very recent interview provides some starting points. By claiming that the values of Islam are specifically favorable to science, he raises the stakes, and makes some statements which even those who are quite committed to promoting better understanding of Islamic science might find difficult to accept. The whole interview is worth reading, since as a scholar he can not only score good debating points but consider difficult questions such as the decline of Islamic mathematics after the 15th century. And he makes a more limited but important point, which has indeed been well appreciated, for example, by Kennedy. That time has a particular value in Islamic observances, which calls for the application of science. Science was an important dimension of the Islamic city. One element was the timekeeping in the mosques. Astronomy was necessary to view the lunar crescent for religious purposes. It must not be forgotten that each of the large mosques had an astronomer associated with it. In fact, few religions have given practical mathematicians so much to think about as Islam, with its lunar months which start at the moment when the new crescent is visible, its carefully defined 5 prayer times a day, and its fast which ends at dusk. Astronomers worked tirelessly on the improvement of their tables, developing the Ptolemaic and Hindu astronomy into a much more efficient instrument, but as early as the time of Ibn Qurra, who wrote on the difficult question of the first visibility of the moon's crescent. They came to realize that their understanding of atmospheric phenomena always left some doubt about the key questions of what one could see. The science of time was of course useful beyond a religious context, and similarly mathematics was important to the flourishing societies throughout the Islamic world insofar as it helped with commerce, surveying, architecture, and the various practical arts, and also in geography. The understanding of the known world. In this religion enters again, and the 10th century universalist Al-Bir'un I can stand as a central figure, whose coordinates of cities made possible a general understanding of how the various widely scattered centers were related on the globe. Using a well-developed understanding of geometry on a sphere. Both Al-Bir'un I and his modern commentators have claimed more, that such knowledge was essential for religious purposes, since to design the layout of a mosque correctly it was essential to determine the Qibla, the direction of Mecca where the faithful should turn for prayer. As he says, ETS point out the great need for ascertaining the direction of the Qibla in order to hold the prayer which is the pillar of Islam, and also its pole. God, be he exalted, says, so from wheresoever thou startest forth, turn thy face in the direction of the sacred mosque, and wheresoever ye are, turn your face thither. The mathematicians may well have thought their knowledge essential, but mathematicians are not always as important as they think, and George Sarton pointed out in 1933 that many medieval mosques in North Africa and Spain have incorrect alignments, despite the flourishing state of mathematics in those countries. This problem has recently been cleared up, it appears, in a detailed study of legal writings and of the mosques themselves by Monica Reyes. 12. The answer is interesting for the light it throws on the status of mathematics. In fact, Islamic lawyers pointed out that the complex mathematical methods were sometimes uncertain, particularly in the case of longitude, and not accessible to the mass of the faithful, as they should be. They therefore allowed recourse to simpler definitions, which of course gave more approximate directions for prayer. This is not to say that Al-Bir'un I and others were irrelevant. There must have been cases of mosques where the Qibla was determined by mathematics. However, here, as elsewhere, its use could be contested and the idea that it was imposed by religion certainly begins to seem simplistic. This example can serve as a cautionary tale on the limits of the usefulness of mathematics, which was certainly important enough in the world of medieval Islam. As we shall see, Marxists tend to claim that mathematics is driven by the demands of society, and mathematicians, when it suits them, claim that they are doing vital and useful work. However, if much of the organization of Islam was favorable to science, there were certainly times and places when science could be dispensed with, even treated with hostility. 13. To make a parallel, Descartes, Pascal, and Galileo were no less good Christians than their predecessors. If they found that their religion could be harmonized with a rational and practical scientific outlook, the cause is perhaps to be found in the ideological climate, or what Marxists would call the relations of production. Accordingly, a particular difficulty in the statement with which this section opens is that Rashid seems to be treating Islam, as religion and philosophical outlook, as homogeneous in its positive effect on the sciences. It will be interesting to see how other specialist historians react. Exercise 9. What would be necessary to know in order to determine the Qibla? Given the necessary information, how would you do it? Appendix A. From Al-Khw Arism I's Algebra. A root is any quantity which is to be multiplied by itself, consisting of units, or numbers ascending, or fractions descending. A square is the whole amount of the root multiplied by itself. 12. La alquibla en alandalas y al maghrib al aqstada, reviewed in ISIS 94. 13. Again, Rashid produces good examples to show that an anti-science outlook cannot be equated with religious orthodoxy, but there were trends within orthodoxy which were opposed to science. A simple number is any number which may be pronounced by itself without reference to root or square. A number belonging to one of these classes may be equal to a number of another class. You may say, for instance, squares are equal to roots, or squares are equal to numbers, or roots are equal to numbers. I found that these three kinds, namely, roots, squares, and numbers, may be combined together, and thus three compound species arise. That is, squares and roots equal to numbers, squares and numbers equal to roots, roots and numbers equal to squares. Roots and squares are equal to numbers. For instance, 1 square and 10 roots of the same amount to 39 direms. That is to say, what must be the square which, when increased by 10 of its own roots, amounts to 39? The solution is this. You have the number of the roots, which in the present instance yields 5. This you multiply by itself, the product is 25. Add this to 39, the sum is 64. Now take the root of this, which is 8, and subtract from it half the number of the roots, which is 5, the remainder is 3. This is the root of the square which you sought for, the square itself is 9. We have said enough so far as numbers are concerned about the 6 types of equation. Now, however, it is necessary that we should demonstrate geometrically the truth of the same propositions which we have explained in numbers. Therefore our first proposition is this, that a square and 10 roots equal 39 units. The proof is that we construct a square of unknown sides, and let this figure represent the square which, together with its roots, you wish to find. Let the square, then, be above which any side represents one root. Since then 10 roots were proposed with the square, we take a fourth part of the number 10 and apply to each side of the square an area of equidistant sides, of which the length should be the same as the length of the square first described and the breadth 2.5, which is a fourth part of 10. Therefore, for areas of equidistant sides are applied to the square of each of these the length is the length of one root of the square of and also the breadth of each is 2.5, as we have said. These now are the areas C, D, E, F. Therefore, it follows from what we have said that there will be 4 areas having sides of unequal length, which also are regarded as unknown. The size of the areas in each of the 4 corners, which is found by multiplying 2.5 by 2.5, completes that which is lacking in the larger or whole area. Whence it is we complete the drawing of the larger area by the addition of the 4 products, each 2.5 by 2.5. The whole of this multiplication gives 25. And now it is evident that the first square figure, which represents the square of the unknown, and the 4 surrounding areas make 39. When we add 25 to this, that is, the 4 smaller squares which indeed are placed at the 4 angles of the square of, the drawing of the larger square, called GH, is completed. Whence also the sum total of this is 64, of which 8 is the root, and by this is designated one side of the completed figure. Therefore when we subtract from 8 twice the fourth part of 10, which is placed at the extremities of the larger square GH, there will remain but 3. 5 being subtracted from 8, 3 necessarily remains, which is equal to one side of the first square of G, B, H, AC, E, F, D. Figure 7 LKHW Arism I's second picture. A, B, F, E, C, D, G. Figure 8 the figure for th a bits proof. Compare figure 4. ABCD is the squares of the problem, and rectangle DE is the roots. Their sum is the numbers, and is known AF equals FA. Appendix B th a bit IBN Kura. The first type is this, square and roots equal to numbers. The way of solving it with the help of the sixth proposition of the second book of Euclid's Elements is as follows. We take for the square a square ABCD, and let B be a multiplicity of units which measures a line, equal to the given number of roots. We draw the rectangle DE. Then it is clear that the root is AB, and the square is ABCD. In the domain of arithmetic and numbers, it is equal to the product of AB with a unit which measures a line. In this way, the product of AB with a unit which measures a line is equal to the root in the domain of arithmetic and numbers. But B is such a number, equal to the given number of roots. And so the product of AB with B is equal to the roots of the problem in the domain of arithmetic and numbers. But the product of AB with B is the rectangle DE, as AB is equal to BD. So the rectangle DE is itself equal to the roots of the problem. And so the whole rectangle CE is equal to the square and the roots. But the square and the roots are equal to a known number. So the rectangle CE is known, and it is equal to the product of AE with AB, as AB is equal to AC. So the product of EA with AB is known and the line B is known, as the number of its units is known. In this way, the question leads to a known geometrical problem, namely, the line B is known, it is produced to AB, and the product of EA with AB is known. But in the sixth proposition of the second book of the Elements it is shown that if the line B is divided in half at the point F, then the product of EA with AB together with the square on BF are equal to the square on AF. But the product of EA with AB is known, and the square on BF is known. Hence the square on AF is known, and so AF also is known, and if from it is subtracted BF, which also is known, there is left the known AB, that is the root. If we multiply it by another equal to itself, we find the square ABCD is known. This is what it was required to show. Appendix C. From Al-K-I, The Calculator's Key, Book 4, Chapter 7. On the measurement of bodies with regular faces. There are 7 bodies. Al-K-I considers not only the usual 5 but 2 semi-regular solids, which have their faces all regular and regularly arranged, but not all the same. The first contains 4 faces, which are equilateral triangles in the sphere, that is, it is the body bounded by 4 equal equilateral triangles. It appears as a pyramid with a triangular base, and is made up of 4 pyramids, whose bases are its faces, and whose vertices are at the center. The measurement of this is as follows: take the square on the diameter of the circumscribed sphere, and find the root of 2/3 of it, and also the root of half the square on the diameter, and the first will be the side of the base, and the second the height of the triangular side. If we multiply one of them by half the other, we find the area of one side. If we multiply this by 2/9 of the diameter of the sphere, we find the volume. Another way. We multiply the diameter once by 0.48, 59, 23, 15, 41 fifths, and we obtain its side, and another time by 0.42, 25, 35, 353 fifths, and we obtain the height of the triangle. And do the rest as before. The main relation S equals d of the side of the tetrahedron to the diameter of the sphere is to be found in Euclid 13.13, and so, common knowledge among the savants at Samarkand, which is presumably why Al-K-I feels there is no need to prove it. As has been said, his book is an exposition of methods, not of proofs, although from his other works we know that he could produce serious proofs when needed. As for the actual figures, in sexagesimals to fifths, they follow from the standard method, which he has set out earlier. 4. Extracting square roots, the first number is 23 and the second 12. It is interesting to compare the second figure with the Babylonian version on the Yale tablet, which has the Figure 10 Al-K-I's table. Value 42, 25, 35. Was the same method used? Above is the table which Al-K-I gives of the regular solids. Exercise 10. Take a tetrahedron with vertices. Why is this a regular tetrahedron? What is the length of a side? What is the diameter of the circumscribed sphere? Verify the relation which Al-K-I gives. What do his other statements mean, and can you check them? can you do any of this without using coordinates? Solutions to exercises. 1. Clearly, it denotes an odd place, and the point is that your starting point is to look at the number up to the last odd place. The whole part of the root of this number, which is a single figure, gives you the first figure of your answer. You now have 2 as the root of 4, the largest square less than 5. You subtract its square from the 5, and drop down the rest, giving 176. You now double the 2 and put it under the 7, so it is effectively 40. Al-Uqaidi's I's expression means that you are looking for an x such that 40x added to x exhausts the 176 you have left. In other words, x equals 176. In fact, this is satisfied by x equals 4. The method is simply using the usual formula for, with a equals 20 and b equals the unknown x. If this is slightly confusing, try some other 3 and 4 figure squares. Then see how it generalizes to larger ones. 2. As in Chapter 2, let us use algebra to simplify. Call the length AB a. Then BC equals a, BD equals a 2, and so CD equals 5. Hence by construction, DE equals CD equals 5. So AE equals a 2. This is the right length for the golden section, construction of Chapter 2. The triangle ABG whose sides are in the ratio 1, 2, 2 has angles 36, 72, 72, and the construction proceeds as required. 3. Al-Khwarizm I gave 6 equation models, and these were always followed by his successors through the medieval and early modern period. There are 3 trivial ones, roots equal to numbers, roots equal to squares, and squares equal to numbers, and 3 serious ones, roots and squares equal numbers, roots and numbers equal squares, and squares and numbers equal roots. Again, because there must be a positive solution, the form squares and roots and numbers equals 0 is excluded. For AD is equal to AB plus BD, or A plus B. The rectangle AD by DB in Euclid's language means the area of a rectangle whose sides are equal to AD and DB, so it is the product B. Since C is the midpoint of AB, CB equals a 2, while CD equals CB plus BD equals plus B. From this the statement follows. 5. Al-Khwarizm I's method starts by having the roots, result 1. Square this, result 1, add to 1, result 2. Now our problem is to take the square root. If we can, subtract half the roots, that is, 1, and get the answer 21. The line B has length 2, and we must construct AB so that the square on AB and the rectangle ABB are equal to 1. We divide B in half at F, so BF equals 1. Euclid 2.6 says that EAAB together with the square on BF equals the square on AF. So we construct a square of area 2, its side is AF. Subtract BF, and you have the result AB. This depends on the fact that you can construct AF, whose length is 2 geometrically without saying what the length is. 6. Call the amount x. If 10 is added to an amount, and the amount is multiplied by the root of 5, we have 5. This is said to be equal to the product of the amount with itself, that is, to x. So, 5 equals x as stated. By the usual rules for quadratics, write it as x 5x 10 5 is equal to 0. Then the solution is x equals 125 plus or minus 5 plus 4.10. 5. Obviously for a positive solution we want the positive root, and a slight rearrangement of the expression puts it in the form given by Abu K. Emil. 7. Since sin 30 equals, setting sin 10 equals y, we obtain the equation for y plus equals 3y. 8. Rather than to the division, consider the 2 tables shown in the figure. The first shows simply the dividend p arranged in columns according to powers, with coefficients, and below it the divisor q is equal to 2x plus 5x plus 5 plus, shifted up by 3 places, ready to be multiplied by 10 and subtracted. The second table has the 10 in the cube's place of the top row. In the second row are the coefficients of p10x, q, and in the third q again, this time shifted up by only 2 places and ready to be subtracted again. The process concludes when Al-Samael finds that his final remainder is an exact multiple 2x times q, and we can stop. 9. This is a slightly hard exercise in spherical geometry. We have to know our latitude, say A, the latitude of Mecca, say B, and finally the difference between our longitude and that of Mecca, say C. We then have a spherical triangle ABC. The angle at the pole is C, and the two adjacent sides are A and B. The Qibla is determined by the angle which the line from us to Mecca makes with north, the angle B in the figure. The sine formula for spherical triangles. Sin B equals sin C would give us B if we knew C, since we know B and C. But we can get C from the